Good afternoon, everyone. And thank you very much for joining us for today's webinar brought to you by Mitsubishi Electric Heating and Cooling. My name is Ken Lascastle. I'm the Chief Operating Officer with the Mechanical Contractors Association of Canada. And I'm very pleased to be joined today by Will Elleridi. He's the Sales Manager for Ventilation Products at Mitsubishi Electric Sales Canada. Today, Will is going to be providing some of his insights on a very important topic, and that's indoor air quality using high efficient ventilation systems. With more than 10 years of experience in HVAC, Will has extensive knowledge on applied ventilation equipment and energy recovery ventilators. And we're all looking forward to him sharing his insights with us here today. So I know we're going to save some time at the end of the presentation for some questions. So I would encourage you to use the chat function and the Q&A function built into Teams throughout the presentation if you have any questions that you'd like to have answered. But without any further delay, Will, I'll turn things over to you.
Thank you so much, Ken. Appreciate it. I'm just gonna go to presentation mode here. Screen is good.
Yeah, looks great.
Awesome. Okay. Yeah, thanks for the intro, Ken. Yeah, as you were saying that indoor air quality solutions using high efficient ventilation systems is a topic I selected because it's been talked about more than ever right now, for obvious reasons. And I want to do a little bit of expansion on how to tackle this issue using ventilation systems and how to use it in the most efficient manner. Since ventilation has been a big focus on indoor air quality improvements, I'd like to take an opportunity to emphasize how we can increase ventilation in commercial and residential spaces by not necessarily increasing building operating costs. So I'd like to start off with this slide in order to illustrate how important indoor air quality is by putting into perspective of how much time we actually spend indoors. Society spends as much as 90% of our time indoors, exposing us to pollutants. Poor indoor air quality can contribute to low quality productivity for workers and even school absences for children. Sometimes pollution can be generated 2 to 5 times more than what actually outside has due to many different reasons, which I'll go through in further detail in a minute. Looking at some traditional older heritage buildings, what they would rely for ventilation is simply opening a window or a door, which is infiltration method. So let the building naturally breathe by itself or having natural ventilation. So this is obviously not ideal because different weather conditions won't allow you to always just open the window, obviously, because it could be either too hot or too cold. Looking at modern buildings, more modern buildings are well manufactured using many different types of materials, like literally thousands of different types of materials. And the problem with that is that there's after the building is built, or a house, let's say, for example, it's going to continuously off-gas these new materials for almost 2 years, even sometimes. There would be CO2 and even VOCs that would be off-gassing in these buildings, even like paint that would be freshly painted from the walls. So these tightly sealed buildings would require some forced air to have fresh air into the space itself. And you can't always just let the building breathe on its own. So looking at indoor air quality importance, you might have seen this before, is the Swiss cheese model. So there is 5 different steps on how to tackle indoor air quality and making it improve. Number 1 is it's been confirmed for many different studies that increasing the ventilation in spaces from, let's say, the standard 3 to 6 air changes per hour to 9 to 12 air changes per hour greatly reduces the amount of air pollutants that are going to be present in the space. Number 2 is humidity control. A lot of people don't really regard this very often, but it is still very important. And maintaining comfortable humidity, which is the ideal zone of 40 to 60%, is where we need to be for ideal human comfort. Number 3 is high efficiency filters. Increasing filtration can help block harmful pollutants getting injected back into the space, whether it's from outside or recirculated air. Additional protection, not as a primary protection, but additional protection as a secondary or third option, is adding UV light UV lighting or bipolar ionization for air purification. And finally, number 5 is HVAC maintenance activities. So once a building is commissioned, it should not be ignored because there are many different times where, from my own experience, going to a roof of a condo building and seeing that how the filters are like haven't been changed in more than a year, and you can just see a huge thick layer of dust piled up onto it. And by that point, it defeats the purpose of putting in fresh air into the building because it's carrying those pollutants along with it by causing the filters to get warped because the amount of air pressure is going to be sucking in those filters. So that's just an example. Proper maintenance of these mechanical equipment on the ventilation air handling units or ERVs is very critical. Now, looking more into energy recovery ventilation, which is one of the high efficient ways of ventilating a space, you don't just use a duct ventilator, whether it's an exhaust for a bathroom or exhaust for a kitchen, and then builds that negative pressure and allows infiltration into the building through a window or a unweathered sealed doorway. But instead, you're controlling it more with an energy recovery ventilator, in which allows you to bring in fresh air from outside and exhausting old stale air at the same time. So 1 CFM in, 1 CFM out. And at the same time, you are pre-treating this air by using the heat exchanger that it's integrated inside the unit. Now, the benefits of proper ventilation using ERVs is very different types. Well, number 1, it deodorizes from various types of smells or odors that are present in the space, such as cooking, pets, or any type of chemicals that are being used in the space that, used for cleaning, whether it's like Lysol or bleaches or anything like that. So you're help deodorizing it that way by replenishing that air more often than usual. And finally, reducing excess humidity, which creates from the hot showers, people, and kitchen cookware, such as tea kettles, etc. By using an ERV, you're helping to balance that humidity level from the high to low side. So controls from different room temperatures and reduces air pockets, heat trapped in upper levels of the home. So this will also help regulate the temperature throughout the house by circulating the air and bringing fresh air into the space. Now, looking more into the relative humidity importance, and as I mentioned, that ideal range, the human comfort range, is around 40 to 60%. This reference is a website called 40to60rh.com. This is conducted by Dr. Stephanie Taylor, which is the infection control consultant at Harvard Medical School. And there were many studies being conducted on studying the various humidity levels within the space and how different particles are reacting and how they inhabit the space. So this goes to show that over here on the left side, where it's very dry, 10%, 20%, 30 to all the way to 40%, you see that viruses, bacteria, they're more prevalent in these very dry environments. While in very moist environments, ranging between 60 to 100%, they pretty much come back in very wet environments, which also encourages mold growth, which we don't want either. So looking at dry indoor air, you see the 0 to 40%, it affects your respiratory immune system. So basically, if you breathe in really dry air, it has those particles free floating around the breathing zone area, which is right in the middle picture over here. So the drier it is, the more free floating the floating time of these viruses or any type of VOCs that are present in the space. Meanwhile, if you're in the 40 to 60 range, these airborne particles are actually attaching themselves to moisture particles, which stay out of the breathing zone because become too heavy and basically drop down and lower to the ground. And the survival time for the viruses are actually more prevalent in drier spaces and as well as moist environments. Looking further into the studies, you can see the infection rates were at the lowest when the indoor relative humidity is between 40 to 60. So respiratory issues, gastrointestinal, urinary tract infections, cellulitis, and even eye infections greatly drop down once you approach the 40% range, and then slowly starts to go back up once you're past the 60% range. So if you want to learn more about that, the website is over here at the bottom, 40to60rh.com. Now, looking at the ASHRAE standards for ventilation, we follow, as a manufacturer and consultants, follow the ASHRAE 62.1, which is the ventilation for acceptable indoor air quality, 62.2 for residential buildings, and the ASHRAE 90.1, which is the energy standard for buildings. This is also very important because you want to be able to ventilate space the most efficient way. So you may be familiar with this ventilation guide from ASHRAE 62.1. Depending what type of application you have a certain criteria to meet in order to meet the minimum fresh air requirements. So I boxed out a typical application here, which is an office space. So what they say for a typical office space is you have to account for 5 CFM per person, which is right over here. I'll just put my laser pointer. So here's 5 CFM per person. And if you know the square footage of the space, let's say number of occupants occupying the space per 1,000 square feet is 5 people, and 17 CFM per person if it's combined indoor air rate. So if you're a service contractor and you are looking to give some advice to the building owner of what they need to do in order to improve or retrofit a building that they're taking care of, it's ideal to look at this table. We're more than happy to work with you on that, obviously, because I do this all the time to help come up with the ideal fresh air requirements used for that space if it does not have an air handling unit or an ERV. Now, moving on to looking at the concept of the, not sure why it's got stuck here, my slide. I'm sorry, just give me 1 second here. Okay. Yeah, so looking at the ERV concept in 2 different scenarios, one in the summer and one in the winter. So what we're doing is pre-treating the air in the summer. So instead of bringing really hot, humid air into the space, we are pre-treating it by pre-cooling, allowing the heat to absorb from the exhaust side and exhausting it back outside instead of back into the inside. So typically 36 degrees Celsius of hot air from outside is getting pre-treated to have pre-cool down to 24 degrees Celsius. And in the winter time, it's pretty much reversed. So instead of pre-cooling, we're doing a preheat. So 0 degrees Celsius coming into the space, passes through the heat exchanger and preheats it up to 16 degrees Celsius. And what that does is puts less load on your mechanical equipment to do heating or cooling, which reduces the operating costs, of course. You know, ERVs for residential buildings have become mandatory since 2017 anyway, so every new build will have an ERV in it, size for the number of bedrooms that it has. But if it's a older house, it will not have it. So we do encourage all the older homes built pre-2017 to put in a ERV. Now looking at more of a study here at a preschool facility, how the CO2 levels were shaping up to be throughout a day, before having an ERV installed. So looking at the ASHRAE limit, CO2 limit, and then the OSHA limit, you're seeing that the CO2 levels are going way past those limits because there's no source of fresh air equipment or ventilation equipment. Now that's before the ERV. Now after installing the ERV, these CO2 levels are very well maintained and goes below both of these requirements. So as you can see that from 6 a.m. to 6 p.m., these CO2 levels are very well maintained below the limit. The reason why there's that spike over here is that the equipment is probably turned off once the school gets, it goes unoccupied mode basically. So if there's any maintenance people in the space or whoever, if there's parent-teacher night or whatever, sometimes they would spike up to that level. But regular occupied hours, that's where it matters the most. That's where most people be occupying that time frame. Now, looking at the energy recovery principle, some of you may already know this concept, but just looking into more detail. So for those that don't know, what we what we typically design for here is these are static core heat exchangers with a cross flow design, using alternating layers to separate two airstreams. The membranes that divide these two airstreams is what allows the heat transfer from one side to the other, which is sensible heat, and the transfer of humidity, which is latent heat. This humidity transfer is at a vapor state from the high side to the low side, as already mentioned. So there's other different types of ERVs, by the way. So there's the cross flow design, which I gave an example right now. There's also a counter flow design. There's also energy recovery wheels. Same with heat pipes. So there's various types of energy recovery or heat recovery devices out on the market. So it really depends on what type of application would fit best. Now, looking at the membrane from a molecular level, see the concept is using a paper-like material. So an ordinary paper that you see on the left side here, it does transfer humidity and temperature. It's like rolling up a piece of paper and blowing hot air into it, and then you feel the other side of that paper is getting hot. That's pretty much the concept that we're talking about here. The problem with that is that that piece of paper would allow other harmful pollutants to pass right through it because the molecular structure is too spaced out. On the right side, you see that what we use as a specially treated paper made of cellulose fibers, which helps block out those harmful pollutants like CO2 and NO2, while only allowing the water molecules to pass through from as a vapor state. So this is what we want to achieve here, because when the two airstreams are passing through, one is exhaust and one is supply fresh air, we want to have at least a near zero cross-contamination situation here, because at the end of the day, if there is cross-contamination, we are defeating the purpose of, providing fresh tempered air here. Now, the ERV versus HRV. So the ERVs are energy recovery ventilators, as explained. HRVs are heat recovery ventilators. Now, some people get those terminologies mixed up, so that's why I included this slide here, that not all HRVs are HRVs, but not all HRVs are ERVs, because what HRVs cannot do is transfer humidity. So the various areas and climate zones in North America, we are still able to use ERVs, even if it's like moderate temperatures. So ERVs would work best in cold climates and hot, humid climates, basically more extreme temperatures, in order to allow for a transfer of the delta between the supply and the return side to have a higher effectiveness rate. And same with the humidity levels. If it's really, really dry outside, you want to be able to not bring in dry air, but help recover the humidity built up that's already inside the space. Now, ERVs versus HRV in terms of frost thresholds, ERVs actually have a higher frost threshold because of their ability to transfer moisture in a vapor state, which delays the process, delays the consequences of the frost building up on the membrane. So because it's able to transfer that humidity levels, it delays that process. So for example, on the HRV, we have our frost threshold at -12 degrees Celsius, while the ERV is at -17. So the higher effectiveness or the higher efficiency the ERV is, the lower frost threshold it's capable of doing. Now, moving on to the types of applications and when to use different types of ventilation equipment, broken down in two categories, which is the centralized or decentralized ventilation. On the left is a centralized ventilation system. Typically, what you'd be familiar with is seeing a DOAS unit or a makeup air unit, typically located on the roof of a building, which has duct risers that can branch out into different zones, providing fresh tempered air that way. Or sometimes it does pressurization in a corridor and allows the infiltration of fresh air to go into each suite. So basically, this would allow to prevent any odors that would be present in the hallways caused by cooking, for example, and other types of chemicals that could be built up within the suite. So by pressurizing the corridors, you're able to push that those smells, staying into the suites and relying on the bathroom exhaust to do all the exhausting that way. Now, for decentralized ventilation, we're using in-suite ERVs or decentralized ERVs as a unitary device. typically used for small to medium-sized buildings, but now we're seeing more and more of it in condo buildings where we're seeing a smaller makeup air unit on top of the roof. Instead of pressurizing the corridors, it only supplies fresh air to the minimum standard and relies on these individual ERVs to take care of its own fresh air requirements for that suite. So for decentralized ventilation products, what Mitsubishi does carry is our Mitsubishi brand, which is called the Lascastle. This is typically for light commercial type applications ranging between 300 to 1200 CFM. And there's a Renewair product that we carry as well, which has been a long-term partner of Mitsubishi, which they do also use the Mitsubishi core. So you're getting the same efficiencies of up to 80% on the sensible side and up to 70% on the latent side. The good thing with Renewair is that they have a very wide range of airflows from the residential side of 40 CFM all the way up to 11,000 CFM on the applied ERVs for the commercial type applications. Now looking at the Lascastle, looking at the guts of it, we have the core that's right in the middle of the unit, and you have an exhaust fan and a supply fan and two thermistors, which is used to measure the in and out temperatures and providing output for the controller of defrost function once you're in the really, really low ambient temperature ranges. And it also determines whether to open and close the bypass damper, which allows for free cooling. And that damper is integrated in the unit right here as well. Looking at different controls options, we can have it fully integrated into the Mitsubishi VRF system. So if you have a central controller, which is the AE200 controller, by controlling all the fan coils, you can also control the ERVs as well. You can control it through an AE200 controller, or you can have it individual with this PZ62 controller. It's a local controller that can be mounted on the wall and have it individually controlled that way as well. So you have different options of doing it that way. And I'm going to be talking more about how we can integrate controls and having these systems working together and, supplying heating, cooling, and ventilation in the most efficient manner. But moving on to the next topic, point here, what I mentioned earlier, is using high efficiency filters. Using high efficiency filters is obviously a huge tool to use in order to improve indoor air quality. We know the importance of indoor air quality from an HVAC perspective. Here we can see that filtration, typically a standard is a MERV 8. We're seeing more and more of MERV 13 filters being used in commercial applications. Now, this table is taken from ASHRAE's 52.2, which is the filtration efficiencies, which is ranked from 1 to 16. And there's 3 columns here in different ranges. And these are the size of the particles from 0.3 to 1 micron to 1 to 3, and then 3 to 10 microns. So as you can see here, the smallest particle size will not give any performance data for the first 10 MERV rated filters. So you'll have a 20% efficiency of removing these smallest particles starting from a MERV 11. So that's why MERV 13 is becoming more and more popular, even though it's 50% efficient. It's always encouraged to use higher efficiency rating of filtration. But the typical range here is the range 2. So you can see here that MERV 8 or MERV, the range 3 is MERV 8 can remove 70% of the particulate matter by utilizing this type of filter. Now, different filters that were used for the Lascastle, which is the standard filter. This is equivalent to a MERV 7. This is a MERV 14, and this is a MERV 16 with an advanced high efficiency filter. And then for larger air handling systems, you can use a cartridge type filter, which is typically 12 inches in depth. This is could be a HEPA filter, or which is rated for MERV 14 or MERV 16. And then you can typically see also the bag type filters. So increasing ventilation and filter efficiencies are great solutions, but what about energy consumption? So how do we, take care of that trade-off? Well, what's becoming more and more popular is the type of motors that we're using. The The standard motors that are using are the PSC motors, which is the permanent split capacitors, which are typically 60% efficient. So this is a type of motor that's relatively simple. It has a run and wind windings and the external run capacitor, and it's designed to only do two things. It turns on and off. The electrical output of the motor is not controllable, and there are no speed variances to control. So since the motor operates at a consistent speed, the use of energy is constant and the efficiency is lost. So basically, you cannot turn down the airflows with a PSC motor. Basically, you're only getting on and off, or if anything, you get two speeds only. However, what we use are the EC motors, which are 80% efficient, which has more rangeability. It's controlled by a microprocessor, which can save energy and improve efficient movement of air through the ERV. EC motors allow for variable speeds that can correspond to the unit's call for airflow, which is a demand control strategy. Now, using us as an example, the RVX, which is our new Lascastle ERV unit that uses DC motors, versus the RX5, which is the older PSC motors that we've had. And looking at it compared to side by side with four different models, which is 300 CFM, 470, 600, and 1200, you can see that the 52% less power being consumed on the 300 model, 65% less, 65% of the total power used for an RX5, and then 69% and 68% respectively. So you can see the savings already here just by switching over to an EC motor. Now, taking it one step further, for better variable airflow control, we can select different airflow settings or speed settings. So the speed settings can range from 25% all the way up to 100% in 5% increments. And on the controller itself, you can set your percentage of airflow for each fan speed. And it doesn't have to be balanced in this way. In this case here that you see, 30%, 30%, 40, 30, or you can actually have more variable variances in the supply and exhaust. So you can have positive pressure or you can have negative pressure in the space. It really depends on what type of application you're using here. So you can definitely play with the fan speeds for the supply and exhaust side. Now, one way to implement a demand control strategy, which is becoming more and more popular, is having a CO2 sensor. And what we have just came out about a year ago or two ago is an integrated CO2 sensor, which gives you indicator lights, which gives you low, medium, or high indication of CO2 levels. And you can actually set those parameters on the controller itself. So for example, you can set the low side to 1500 ppm of CO2. The mid range is 1500 ppm for being present in the space for less than 20 minutes. And then it jumps to high side of 1500 ppm or more if it's present in the space for more than 20 minutes. And that's all configurable within the controller. So here's a screenshot on the bottom right corner here. You can set your upper and lower limit, and then basically set it and forget it from that point. So every 50 ppm that the CO2 level goes up in that space, the fan speed increases by 5%. So this is the precise control that you're getting from the ERV. So instead of over-ventilating a space, you're getting exact ventilation that you require for that space alone. So that, at the end of the day, gives you more improved operating costs. So looking at Renewer's solution as well, you can also implement CO2 sensors, indoor air quality sensors, and even occupancy sensors, which are the most popular. So you can actually set a time schedule to have occupied, unoccupied modes in order to turn on and off the ERV, or having it run in low mode or high mode. And you can also tie it into a BMS system by using a DDC controller. This could be tied into a backnet, whether it's a IP or MSTP protocols on the commercial type units, which is in this case, the EV450, HE, LE, and DM models. Now moving more towards the centralized ventilation. So we already talked about decentralized ventilation using individual unitary ERVs, but now we're getting into more sophisticated equipment, which is the DOA system, the dedicated outdoor air system. So what the dedicated outdoor air system does is it has integrated heating, cooling, ERV, and dehumidification all in one. And the whole point of it is to get that ambient temperature down to the room neutral zone, which is the ideal human comfort range, in order to provide that fresh tempered air that's required. And typically that ranges between 70 to 75 degrees Fahrenheit, and of course, relative humidity of 40 to 60%. So if it's too dry, you want to add simply humidification. And in the summertime, you can do dehumidification using the DX circuit here. Now, there's two ways of installing the DOAS system, which could be integrated with the VRF system, for example. And one way is having a coupled or integrated system, which has the fresh tempered air being supplied by the DOAS unit directly into each fan coil unit. So some fan coil models allow for a 4-inch cutout, which allows fresh air into the fan coil while mixing in with the with the return air. It's really important to supply fresh tempered air, because if you bring in colder or hotter air, we don't want to oversize our VRF system, because that's going to increase the cost as well. So if you bring in fresh tempered air, we're only doing minimal, increases of heating or cooling. So that way you don't have to upsize the VRF system. So typically a fan coil would allow 15 to 20% fresh air into the fan coil unit, while the rest of it would be return air. So it's since it's very well mixed, you're not going to get too much of a variance in temperature and entering air temperatures. But nonetheless, you are getting fresh air into each space, and in a more uniform way. And then we have a decoupled system, which you have the makeup air or DOAS system supplying fresh tempered air through its own duct system. So as you can see here, the supply air has its own diffuser, and then the fan coil has its own diffuser as well. Now, this is a lot cheaper to do as well, because you don't have to have complex controls, which you have the two systems talking to each other to prevent any improper air balancing. In this case, you're just supplying fresh tempered air, and then the fan coil system is on its own closed loop to take care of the additional heating or cooling depending on what the room set point is. Now, there's different advantages and disadvantages of this, of course. The one that stands out, of course, is that you want to reduce the amount of air stratification within that zone. So properly placed supply diffusers is ideal here. So for example, if you're supplying 70-degree tempered air from the makeup air unit, but the fan coil is supplying 75, it's not too much of a difference in temperature that you can really feel it, but sometimes some people can feel it. So if you want to reduce the amount of air stratification, you'd have to strategize where to place those diffusers. And here's just a schematic of how it looks, once you, install both systems. Now, the dehumidification process during the summertime, you want to make sure that you want to get into comfortable space. So looking at a psychrometric chart here, we have outside air, typically for Toronto air conditions here, design conditions of 90 degrees Fahrenheit. And what we want to do is supply fresh air at 72 degrees Fahrenheit and down to 50% RH. So what you do is you pass the air through a DX system, the DX coil, all the way up to saturation point. And then what it's doing here is removing all that moisture, having that moisture dropping into the drain pan of the DX coil. And then after the DX coil, it passes through a hot gas reheat coil, which heats up the air back sensibly to the comfortable 72 degrees Fahrenheit. So here we're going from 62% of relative humidity all the way down to around 45%, which is ideally where we need to be in this case, especially for the summertime. So looking at it from a refrigeration circuit point of view, we're looking at an advanced refrigeration circuit. Now, instead of us sending a full column of subcooled liquid into the VRF condenser to the DOAS DX coil, the system regulates the amount of condensing done by the VRF system in order to create a mixed phase refrigerant that's part liquid and part gas. Now, instead of bypassing the reheat coil, the mixed phase refrigerant flows through the reheat coil, where the rest of the condensing takes place, producing a subcooled liquid. So instead of rejecting that heat into the atmosphere, you want to bring it back into the airstream of the air handling unit in order to reheat that air back up to 70 degrees where we need it to be. Now, because we're using 100% outside air and a packaged DX system, we make sure that we follow the HRI 920 standard. So this is the metric that's used in order to meet the ISMRE numbers. Every selection we use for our DOAS unit will have the ISMRE numbers available in every submittal. So we do follow the HRA standard, especially the one that just came out this year, which is by the DOE. Typically, ASHRAE 90.1 also follows with it. Now, taking one step further than that, having, a standard package DX system with whether it's a gas furnace or electric coil or a hot water coil doing the heating and cooling on the DOAS unit, what's becoming more and more popular is a packaged DOAS system using air source heat pump. Now, what we offer is a 5 to 30 ton solution on the package system. We are looking to expand that even further to 50 tons soon. But for now, we have that option to, supply 5,000 CFM for a non-ERV model or 7,500 CFM for a model that has ERV because its ability to do pre-treating that way. So what this does is having the air source heat pump as a primary heating device in the wintertime while having a secondary backup heat when it dips below 10 degrees Fahrenheit or minus 12 C. So that secondary backup or supplementary heating could be selected as a gas furnace, hot water, or electric coil. Now, because our COP levels are more than 2.5, you are improving the operating cost as well and reducing carbon emissions, which is the initiative we need to meet by 2050 by net zero standards. The unit does also have a defrost cycle integrated through the controller, which is based on the outdoor air conditions as well as the suction temperature. Now, looking at an example of different scenarios of how the air source heat pump works. If the ambient temperature is at 50 degrees Fahrenheit, the VRF coil will handle a full temperature rise, and the electric coil, which is located right over here, is completely off. So even at cold temperatures at 15 degrees Fahrenheit, your electric coil is still off, and the heat pump is able to handle the full temperature rise in order to meet that 70-degree leaving air temperature. Scenario number 2, if your ambient temperature is at minus 5F, your electric coil will be sized to handle the full temperature rise. Because we're in lockout mode for the heat pump, in order to protect the condenser coil, which is the outdoor coil, we have to shut that off temporarily in order to get the, once the ambient temperature rises above, the electric coil will turn off again. And if there's no ERV within the system, sometimes you can have both systems run at the same time as supplementary heating. Now, if there's derated capacity and colder temperatures for the heat pump coil, your electric coil will pick up on the slack as well. Now, looking at, from, a big picture perspective of how often the heat pump system will be on, let's say in Toronto, your average bin weather data, the 4-year average taken from April 2018 to March 2022, how many hours it spends in each temperature range for the full year. We're in full backup mode 189 hours of the year, which is around roughly 8 days. Let's just say give or take, plus or minus 1 day of a week. We're in partial backup mode. So if we're in supplementary mode, we're having both systems being on, we're at around 80 days of the year. And then full air source heat pump mode, that's more than half the year of 215 days. So it's pretty much a no-brainer to use an air source heat pump in order to supply fresh air from a ventilation perspective here. We know that VRF, air to water heat pumps are becoming more and more popular. Using the TGS4 standard, heat pumps are becoming more and more of a standard to use here. So from a ventilation perspective, this is probably the best solution to use. Now, you can still control the DOAS unit in a very efficient manner by using a demand control strategy. So just using 4 examples here in order to control it, you can use it as a duct pressure control, which modulates the supply fan using a VFD, which has a static pressure controller, could be mounted in the space or in the return air duct, and will modulate based on the supply, based on the pressure of the system. So if it's a condominium using a building static pressure, it'll modulate the fan speed so it doesn't overpressurize the corridors. So it ranges between 50 to 100% of airflow. And same thing with CO2. Using a CO2 sensor, just like how I explained in the velocity model, This would be good for, applications such as auditoriums or gymnasiums, where if you have a whole influx of people occupying the space at once, you will turn up the VFD all the way to 100% in order to reduce the CO2 levels. Otherwise, if it's unoccupied, you can turn it down all the way to 50%. Same with network control. If you want to tie it into a BMS or a BACnet system, you can do it that way for more usable controls. Or you can tie it into our VRF system. So if you have a VRF system from Mitsubishi, you can actually tie in the same controls that way. You can have multiple addresses for the fan coils like this. So here we have 4 fan coils, for example, but you can have a 5th one for the DOAS unit on the AE200 controller. If you don't want to use the MNet from Mitsubishi, you can actually have standalone controls, because the DDC controller does come with a integrated web user interface. So this is standard. Once you connect it to a computer through Ethernet or Wi-Fi, you can see that in the software itself, the display, that you can see the live action of how the unit is operating. So you can see if the dampers are open or closed, heating and cooling information, what speed the VFD is running, and any other sensors that are attached to the unit. And you can also get trending capabilities. You can see like different alarms, service by getting trending from how the unit was performing in the past 7 days by doing minor tweaking that way. So you can definitely have full experience on to control the unit that way if it is standalone controls and not necessarily going to the unit itself. You'll also get a mirror image of the Corel controller display, which you can see all that information within the software itself. Now, looking at the 4th point that I was mentioning for indoor air quality improvements is the additional protection of air purification. So what we do have in our DOAS system available, you can have integrated UVC lighting and bipolar ionization. So we know that air purification and UVC lighting is the most popular. We can have now selected on our premises model, which is our DOAS unit, which is the name for it. So these UVC lights, the air that passes through the UVC light can inactivate these microorganisms that could be harmful to our health. And on the larger units, you can see that the lights are installed between the filters and the DX coil, downstream of the right before the blower motor section. So this is an ideal place to install it, because if there's a drain pan there where the DX coil, if for whatever reason the P-trap of the drain is clogged up, you will have standing water there, and which is not desirable. That UVC lighting will help inactivate those microorganisms and prevent any mold growth from that point until the maintenance contractor comes in and frees up the drain from that point. So it's used for disinfection overall, and it does come with a safety switch, which when you open the doors of the air handling unit, the lights will turn off. So it will not be harmful to your eyes, if once you open the doors, because of that safety mechanism already installed in place. The second option for air purification is bipolar ionization. It's not super popular. It's not as popular as UVC lighting. Number one, there's been a lot of concern about ozone being injected into the space, which is like free particles of ions being injected into the space. But what you should be looking for when using bipolar ionization is the UL 867 certification, which is guaranteeing that no ozone emissions will be emitted into the space. So the concept behind this is simply the needle point ionization was, as the air passes through it, it'll electrically charge these particles, negative or positive ions. And as these ions gets injected into the space, they'll find other particles to attach itself to in order to neutralize its electrical charge. So once it finds those other particles, such as like water particles or any type of other particles, it'll attach itself to it and then basically drop down to the floor or the table, but mainly away from the breathing zone. So it relies on the particles shifting from the breathing zone all the way to the floor, which you can pretty much vacuum up and dispose of. And finally, HVAC maintenance activities. We couldn't stress that enough, that you would need to regularly check the filters of the system. Here's a little diagram here I want to show you. This was taken from ASHRAE 52.2, showing you that the efficiency of a filter over several weeks. So an unused filter, right at the top here, typically is just a little over 70% efficient for a MERV 8 filter. And after 1 week, it starts to deteriorate little by little. And after the 36th week, you'll see that its efficiency levels drop down below 20%, which is not desirable. So regularly changing the filters, regularly lubing the like making sure that the bearings of the blower motors and the energy wheel bearings are also lubed up in order to make sure that they're running very smoothly, and making sure that the drain pan of the DX coil is free from debris. This is extremely important to have, especially when, once your sole purpose of an energy recovery device or a DOAS system is supplying fresh air. So you want to make sure it's performing at peak optimization. So finally, that pretty much concludes my presentation, but I do encourage that if you are interested in this topic, there is the Indoor Air Quality Guide, which is found on the ASHRAE website. This is basically pretty much a collaboration of multiple associations and agencies in creating this guide, which gives you a lot of useful information, such as many links to various resources and studies on indoor air quality, best practices of indoor air quality building design, commissioning and construction, and strategies to achieve improved indoor air quality. This could be very beneficial for service contractors or anybody in general that is able to, do their own design build type projects as well. And how to tackle indoor air quality. So yeah, I encourage you to pursue finding, reading into this guide to learn more about this important topic. And of course, if you have any additional information, you can contact myself. Here's my mobile number, and you can email me at will.elleridi@mesca.ca, and you can find more information on Mitsubishi's website at mitsubishitechinfo.ca/ventilation. And I'll leave questions now, I believe. So thank you very much for listening in, everyone.
Thanks, Will. That was a great presentation. Lots to think about. Certainly lots to consider when you start thinking about your own renovations or even space. As you said, 95% of the time that I spend in my office
That's right.
when I'm
That's
breathing
right.
in. There were a couple questions that came up in the Q&A, so I can read those out to you if that works from your perspective. There was
Sure.
one. In the case of the ASHP MAU, the secondary heat should be sized to provide full heat? Question.
Okay. So yeah, I'm just going to read it here too. In the case of air source heat pump MAU, the secondary heat should be sized to provide full heat. Yes, typically it would, especially if it has an ERV. Now, that's not always the case because there will be a trade-off once you're sizing it for heating, because you don't want to oversize it because you don't want to freeze up the coil during the summertime as well. So there is, there is that aspect we have to consider here, which I have a certain balance when during in heating or in cooling mode. So that's why we do have backup heat, especially when you're getting derated performance in the colder weather months. So hopefully that answers your question. I do see another one here. How often does the air source heat pump and ERV goes to defrosting mode? So that's a really good question. So from testing and units being on, installed on site from a couple of winters, there have been. It really depends on the conditions. If it's really humid or if it's really dry, typically we can say around every 90 minutes it would go into defrost for 3 to 5 minutes. It's not very long at all. But nonetheless, during those 3 to 5 minutes of defrost mode, once it reverses the refrigeration cycle, that backup heating mode is on. So it simultaneously switches on. So there's no delay in providing fresh air into the space. And once it's off defrost, it'll go back to air source heat pump mode.
Had a couple other questions. Well, one was with, and I think you covered this a little bit, so feel free to sort of reinforce some of the statements you said. But do you have a general sense of when an owner would expect to see an ROI on the upfront investment on some of this?
Oh, that's a that's a tough question.
It's a loaded question.
It's a loaded question because there's so many different variables involved. I'd like to start off by starting from out to in, which is the building envelope. It really depends on the building envelope, how old the building is, and how, just by simply, asking how tight are these windows? Is it double pane? Is it triple pane? How many openings are there in the in the building, and even the basement, like how is the heat rising? So it's definitely a loaded question, but like if you're looking at a brand new building, you are looking on average anywhere around 10 years to 12 years of seeing a payback for these types of situations. We have done some studies on that. So especially when you're using ERV, it's definitely a no-brainer because looking at long-term perpetual ownership of a building, let's say for example for a long-term care home, or a rental building, you want to make sure that it's not just like a build build the building and service it for 2 years under warranty and then off you go. So it's being more scrutinized now to use more efficient systems and meeting these criterias, and not just theoretically, but after the building is being commissioned, they will have to run these studies and tests on how the building's actually performing.
The other question that came to mind was for contractors. Are there any additional types of training that they should be considering when it comes to this equipment?
So it does vary for every manufacturer. We offer that ourselves. We do offer diamond designer training in our own facility in Markham, Ontario. We can also do it as a webinar as well. So there is a dedicated ventilation side for duct design and various types of equipment to be used for ventilation. That's our main focus for ventilation. And the indoor air quality stuff is something that I individually like researched myself in order to tie it all together. So it's more that guide I had showed you previously. It's super beneficial, the indoor air quality guide, and it's very easy to find. Just type in indoor air quality guide on ASHRAE, and then you can see it, and it's free to download, and you can see it from that point. And like I said, it displays all the best practices and the commissioning and construction of how to integrate the indoor air quality for a new build. So I do encourage, again, to look into this guide as well.
It's great. Well, I'm not seeing any other questions at this point. So I want to say on behalf of Mechanical Contractors Association of Canada, thank you again for your time, your expertise on that. I think that was a wonderful presentation, lots of information to digest. I know we did a recording of it, so we will make sure that we post it up on the website for people to revisit if there were slides they'd like to see again, or for anybody who would like to share it with a friend or colleague who may have some interest. So again, thank you to Mitsubishi Electric Heating. Can the PowerPoint be shared? Is a question just popped up. Are you okay if we share that PowerPoint, Will?
Yes, I can share this presentation for sure. If you want to email me, I'm like right over here. So I'll be more than happy to send it over.
Okay. Well, thank you again, Will. Really appreciate your time.
Thank you. Thank you for having me. Appreciate it.
Have a great day.
Okay, you too. Bye, everyone.